Okay, we can start, yes. Thank you very much. So here you can see one of our submarine robots. I will try to speak about it today. The main problem with this robot is to know where it is, because under the water there is no GPS. So it has a sonar, and it sends some acoustic waves under the water, and with the echo, we measure distances, and from these distances, it should be able to localize itself. But just to start, I will come back to the lesson. Yesterday, I was speaking about contractors. So what is important with contractors, what you should remember, is that when you want to solve nonlinear problems, you can use interval analysis, classical interval analysis, with the notion, the concept of inclusion function, but and the CVA algorithm, set inverter algorithm. But the problem is that you will have to be set to control the pessimism. If you bisect a lot, then you will have almost no wrapping effect, no pessimism. When you go to high dimensional problem, you will not be able to bisect anymore because you will obtain too many bisections. Then it is possible to control the pessimism using contractors. That's what I explained yesterday. These contractors can work if you have a lot of variables. And excuse me, yesterday I think it was something like this. So contractors work when you have a lot of variables, and you need to combine them in order to up to a fixed point, in order to reach an envelope, a box which encloses all solutions. So first of all, I will now discuss about how we build a contractor. If I have an equation, so an equation here, an equation corresponds to a set. It can, for instance, the equation you have here corresponds to the set of all x and y, such that x plus sin x times y smaller than 0. So when I write an equation, I have a set. Now what I want to do is to transform this set into a contractor, because there is some kind of equivalence between the contractor and the set. So recall here, a set corresponds to something like this. You have here xy, you have here x2. Recall that the set here corresponds to a contractor represented here in blue. Or here, I take a box, and so on. The set associated to the contractor corresponds to all points that are not contracted by the contractor. For instance, if I take this very small box, which corresponds to a point, then if I apply a contractor, I will obtain the empty set. If I apply the contractor to this point, then I will obtain itself. Okay, so there is a correspondence between the contractor and the set. Now I want to explain how we build contractors. Let me recall that we have a catalog of contractors that are available for primitive constraints. What is a primitive constraint? A primitive constraint is constraints that you cannot decompose. For instance, if I write v equal x times y, it is a primitive constraint. Z equals sine of x, it is a primitive constraint. But this one is a complex constraint. How can it be decomposed? It is decomposed as follows. I add intermediate variables. For instance, I will say that this one corresponds to A, this one corresponds to B, and this one, corresponds to C. So I will add new variables. These new variables, A, B, C, and I will transform one constraint into three constraints. Since I have new variable A, B, and C, I will associate domains corresponds to minus infinity plus infinity for A, A, B, because I don't know where they are. For C, it is different. C, I know it is negative, so I will associate this domain minus infinity plus infinity. Now, I have three primitive constraints for one complex constraint, and I will call, in my catalog of constructors, I will call the constructor for the multiplication, for the side constraints, and for the plus constraints. And I will combine these constructors by building the new constructor C equal C1 O C2 O C3, where C1 corresponds to the first constraint, to the second, and to the third constraint. This constructor will make it possible to contract this complex constraint. You understand? So I will now, what I want to say is that if you have a complex equation, it will be easy to build by decomposition. It will be quite easy to build a constructor for a complex constraint. But we can do something more efficient. More efficient is a forward-backward constructor called also HC4 revised. This is the name of the algorithm. HC4 means inconsistency algorithm number 4. And I will try to explain how it works on this simple example. So I have this equation. So x1 plus x2 times x3 belongs to 1. This inequality corresponds to a set. And I want to build a constructor for this set. So of course, I can see like this. I can see the problem with this one. I have a set here in x1, x2, x3, and I have a box. And the contractor will be able to contract this box without removing a single point of S. How can I do that? So recall that I will have some domains for x1, for x2, and for x3, and this box corresponds to the Cartesian product of x1, x2, x3. So how will I do it? First, I will build intermediate variable. This one is A, this one is B. So, of course, what I can write the domains for A. I don't know the domain for A first, but I can write that it belongs, okay, so A is equal to, so it means that this variable belongs to this domain plus this domain. It is the first one. It will also be the case for B equal to A times x3 as represented here. So I know that the variable B belongs to this domain. I also know that B not only belongs to this domain, but also belongs to 1, 2. Why? Because B should be inside. So I have a contraction of the domain for B. This is what we call the forward contraction. Now, I arrive here, and I want to bring back the information from this domain toward x1, x2, x3. So what I want to do is, I have described the forward, and now I will describe the backward procedure, the contraction procedure. So how can I do it? First, I know that A1 is equal to the product of x2 and x3. So I can write, what I want to do is to, excuse me, I will take the second one. I wanted to write b equals to a times x3. Okay, that's what I wanted to write. So because I have this, I want to propagate back the information from B to A and x3. So how will I do it? I will write that A is equal to B divided by x3, and also I will write that x3 is equal to A divided, B divided by A. Since I have this, I will be able to write here, taking this one into account, for instance, that x3 is equal to x3, so it belongs to x3, but it belongs also to B divided by A. It is what I have written here, and it is due to the fact that I have this relation. I can also do the same for A, and also for x1 and x2. So these parts correspond to the backward propagation. Forward, backward. Okay, so backward. If I apply the forward-backward contractor, I will obtain here, because x1, x2, x3 occur only once in the expression, I will obtain, in this particular case, the optimal contractor, which is not always the case, but the contractor will be here convergent, monotonic, and so on.
Excuse me.
Sorry?
Excuse me.
Yeah.
Forward is okay, but when backward, can you guarantee that unique you have got the, I mean, it's 1 to 1 equals 1. When you have backward,
I can guarantee that I will compute. I will have 3 intervals as inputs. I will have 3 intervals as output. What I can guarantee, if I apply this algorithm, I will have a unique correspondence, and I can guarantee that I will never lose a single feasible value. I will not lose any solution. So, I will come back to this example, and I will, another way to see this is to say, to represent by a syntax tree. So here I will take x1, x2. Here I will write A, so plus x3 multiply, and here equal, for instance, or equal belongs, or equal, if you want, to 1 number which is okay. So what here, each node corresponds to a variable, this one corresponds to A, this one corresponds to B. So what I have done is that I have taken the interval for x1, x2 to contract A first. Since A is a new variable, I don't need to intersect by itself. Then I have contracted B. B has also been contracted with 1, 2. Then the contraction has been in this direction and this direction. So what I have done here is a forward propagation from unknowns to the image in a forward step. I have intersected the image and I brought back the information to my variables. Of course, here, one forward, one backward is sufficient to have the optimal contraction, but most of the time, I need to do several forward and several backward. Okay, you understand? You have to ask me, it's not...
Why?
it's quite easy to program, but it's not so easy to understand. But it's important to understand because it's very efficient in practice. Yes?
In case you have the same variable used more than once,
Yes.
the same equation,
Yes.
would you need more than one for the backward?
Yes. You need more. When it's not optimal, it's in practice. The contractor will be monotonic and convergent, but it is not necessarily idempotent. So when it is not idempotent, it can be more efficient to do it several times. But what happens in practice is that I do not have only one equation. So this will correspond to one contractor, but I have also the equation. So I will combine them like this, if I have, for instance, 3 equations. And if I do 2 forward, 2 backward, it means that here I put a square, a square, a square. If I do several times, or infinite number of times, I can do something like this. But after, I also have to put an infinity here to reach the fixed point. But it is always more efficient to have only a unique repetition and not to do it several times for one contractor. Only one repetition, not several repetitions on each contractor. You understand what I mean? For a question of efficiency, only one loop. I will not do it several times up to the fixed point. Okay? It's okay also? Okay, so it was an important algorithm. So what I have explained here, I don't have the laser here. Oops.
Doctors.
No, don't worry. It's okay. So what I wanted to say here is it's always more interesting to put only a single infinity as represented here. I also have some properties that when I have union and intersection, I have some properties. I will not speak about it today, but there is what we call contractor algebra, where we have several properties and contractors that make it possible to combine them in a more efficient way. Okay. Now, what I wanted to say is that if you have an equation or an inequality, what you do, the first step you have to do is to get rid of the set, of the inequality of the equation, and you transform it in a contractor. Then you combine with union and intersection. Now, why it is important to have this approach? Because sometimes you have other source of information, such that, for instance, an information such that the robot is inside the water. Thank you. The robot is inside the water. So it's not an equation. You have a map. You know your robot is inside the water. Here it's near Brest. You have the ocean here, the Brest. Here you have water. You know it is an underwater robot. And you know you are in the water. How you will represent this information? By a contractor. So what is a contractor? In this context, it is this. Before, after contraction. Before, after contraction. So as you can see here, you have water, water. So this one is contracted like this, in this way. So this one, remove all this part, because you know you are in the water. Also the case. This one is not contracted at all. This one contains only land, is contracted to the empty set. Okay. So if you have an information which does not come from an equation, such as this one, you can transform it into a contractor. Now, you may know also that you have at a distance of 1 kilometer from this one. So to be at a distance of 1 kilometer, you will transform into an equation, but this equation can be transformed into a contractor, and you will be able to combine contractors coming from equation with contractors coming from other sources of information. Any information can be translated into a contractor. Okay? So now, excuse me, what I wanted to say is most of the time in the constraints community, so the constraints community is a very large community in the world which work with contractors. Most of the time they formulate the problem as a CSP, constraint satisfaction problem. So you have variables, x1, x10, as you can see. You have domains, which are interval for us, and you have constraints. Constraints is, for instance, something like this. Each constraint is transformed into a contractor, and methods of constraints propagation that are used in this community transform the constraints into operator, will contract the domains up to equilibrium. In the constraint community, x1, xn are rarely real numbers. Most of the time, they are Boolean numbers, so the sad problem, integers, and more they become, I would say, real variables, or also functions, sets, and so on. In robotics, variables, here I explain only the case where variables are real variables, belongs to R, but of course for the SLAM problem, it can be, SLAM simultaneous localization, it can be, for instance, sets or tubes, more general set of variables. So as I explained, I transform the constraint into contractor, and I apply up to equilibrium. That is what I wanted to make this connection with the constraints community. Also, yesterday I have presented you this example with contractor. So you transform the equation into contractors, and you apply up to equilibrium. I wanted also to say you that most of the time we represent what we call a contractor graph. So you have a variable which corresponds to a node, and a contractor which tells you that x will be able to contract y is able to contract x with respect to this contractor which corresponds to an equation. Okay, so yesterday I have presented this example. I will not come back here anymore. I will show you another example to illustrate a problem that can arise when you have a propagation. So, what I wanted to illustrate, if you have several optimal contractors, when you combine them, then the resulting contractor is not optimal. It is a local consistency effect, and I will illustrate on a simple example. So, assume that I want to use a contractor approach to solve this system of equations. Fine. These two equations can be considered as primitive constraints. Okay. I don't know where x and y are, so I just associate R as a domain for x and y. I have, for my problem, I will have 1, 2, 3 solutions. As we can see before, this one will become transformed, this is the first equation, will be transformed into a contractor. So if I apply, I start with a box which is minus infinity plus infinity in both directions. I apply the first contractor, and I am able to remove, thanks to the first constraint, I am able to remove all these two. So now the current box is this one up to minus infinity plus infinity. Now I will consider the second constraint. I will contract, and now the current box is this one. If I apply now the contractor associated to the sign, is it possible now to contract this box? Yes or no? So, what happened here is, if I have a set, okay, if I have a set, for example, like this, a box can be contracted, here for example this one, but a contractor such that each face, which is the case here, touch the set cannot be contracted. For instance, this one cannot be contracted because this face touch the set, this face also, and this face also. This one can be contracted because this face and this face do not touch the set. So they can be contracted, for instance, like this. Okay. Now what happened here is that the sign touch here this face, left, top, bottom, left. So the sign cannot contract this box anymore. This line cannot contract the box anymore because it touched top, right, bottom, and left also. So each contractor is not able to contract the current box. So I will have to be safe. And you can see the contractor for the sign and for the line were both optimal, but the combination of both, even if I reiterate, is not optimal. Okay, so I will have to bisect. It is what we call the local consistency effect. It means that the contractors see each constraint independently and do not see here the combination that they could remove this part, because they have to see globally the constraints in order to be able to remove this part, and this part, and so on. So I will need this bisection. I need here a bisection. The first bisection will make me possible to use some kind of CPR or branch and bound algorithm to apply after several bisection to convert to this solution to show that here you have no solution. But in practice, what I wanted to say is that I will need few bisection because not only because I have several solutions, but also because I meet a new problem, which is the local dependency effect. This problem appears when I have n equation with n unknowns. When I have much more equation than unknowns, this problem disappears. So it means that when I have n equation with n unknowns, I will not be able to deal with high-dimensional problems, I mean 1,000, because I will need bisections. Now, if I work with thousands of variables, but if the number of equations is much bigger than the number of knowns, this problem will not appear. Okay? Okay. So, I don't know, I will not speak about this. I will recall also that what we call contractor algebra is some application I will present later. It can be interesting to combine contractor by union, intersection, combination, and so on. But I will illustrate later. I think that for this lesson, I will stop for this lesson, and I will finish this chapter on a simple example. Imagine, so it's an application, but a simple application that illustrates how we can use in practice with contractor. So I have electronic circuit, very simple. But we can imagine a big robot, a big experiment with many variables. From this circuit, I am able to make some measurements. For instance, I will be able to measure E, U1, U2, I, and so on. Some of them will be measured, some of them will not be measured. So what I can do, I will replace all my circuit by equations using, for instance, the Kirchhoff equation. And this equation corresponds to constraints. Here I have 1, 2, 3, 4, 5 constraints. As you can see, from this constraint, this one and this one, I can prove this one. But I don't care. Most of the time the experiment is so complicated that sometimes I miss constraint and sometimes I have redundant constraints. It's difficult to have exactly the same number of good number of constraints, but I don't care. I just put all constraints I know here. Then I have some measurements. When I have some measurement, it means that I have some ideas on some variables. On A, for instance, I have no measurements on R1 and R2, but I know that they are positive because they are resistor. So because of the physics, I know some domains for some quantities. Now, what is a contractor approach for this kind of problem? I take each constraint and I transform it into contractor. So here I will have 1, 2, 3, 4, 5 contractors. Then each contractor will be able to contract the domains, and I will apply several times up to equilibrium. So of course here I have few variables, but you can imagine that I have thousands of variables. And the method will converge quickly to will contract domains so that I am sure that no solution has been lost. So for this simple example, of course, we I will not show. I use a special solver, and I am able to contract here to this solution. Okay. Just to illustrate how in practice we use a contractor approach. What is important if I want to avoid to have some kind of optimal contraction is to have redundancy in the equation. So most of the time I need more equation than unknown, and it will be the case in robotics because we'll have a lot of sensors. Most of them, for instance, a typical application in robotics is localization. You will have cameras, you will have you measure distance, you know you are in the water, for instance. You have many of information and maybe too many information. So each information is translated into contractors, and the contractors will provide accurate results as soon as I have as many contractors as I want. Okay. So it is finished for this chapter number 3. If you have any question, so now I will start another chapter about robust estimation. So today, I have finished about contractors. I will present robust estimation just to give you an idea of how interval analysis can deal with outliers, which is a typical situation of outliers. I also give you after SLAM, simultaneous localization and mapping, and after I will attack nonlinear control for samples. So let me start with. I wanted to start with a simple example. So the simple example, some kind of exercise. I will try to, which corresponds to a typical application in robotics. So, first of all, I have here two unknowns, x and y, which corresponds to the position of a robot. So you have a robot, you have landmarks, for instance this one, and the robot, which is here, well, let's say here, for instance, measure distances. For instance, it will measure this distance so, of a mark. So it knows that the mark here, you have the landmarks number 1, number 2, number 3. When you measure distance, we are in what we call a range-only approach. It means that we know the coordinates of the landmarks. They are given here. But when the robot is here, it is a localization problem, so the robot has to find its position. The robot knows that it has, the mark is in this circle. He measures also the distance to this one, the distance to this one, and the idea is to know where is the robot. So, of course, since he knows the coordinates, it knows that it is here, it knows that it is here, it knows that it is here, and maybe it will be able to localize from this information of distances. How can I use a contractor approach for this kind of thing? First of all, since I have two unknowns, A and Y, I can perform simultaneous. So we'll define here the set of all feasible solutions. Why I have a set of feasible solutions? Because I do not have exactly circles, but I have rings. Why I have rings? Because the distances are measured with a given accuracy. So first of all, I will build my contractor. So the first step is to transform all information into contractors. So let me consider, for instance, the first contractor, C1, which corresponds to the first measurement. It means, I will take the second one, it will be more because of the zero. So the second information tells me that x, or general case, x minus xa square plus y minus ye square belongs to 22, 23. Okay, so of course this is a constraint, but I transform it into a contractor using, for instance, a forward-backward approach. Okay, now I want to use a CV algorithm. So the CV algorithm, I have just presented it yesterday with inclusion function. How it works now for our problem, since we want to be more efficient, how can we generalize, I will come back later, how can I apply the CV algorithm when I have contractors? I have here x1, x2. I will provide so the solution set that has to be found by CVR is x. So I will provide to CVR not an inclusion function, but I will provide two tests. Two contractors, an inner contractor and an outer contractor. So what is inner contractor, an outer contractor? Outer contractor is a contractor for x. For instance, I give it C out with contract like this, only removing part of the search space that are outside x. What is an inner contractor? If I give this, it will only remove part of the search space that are inside x. So if you want, an inner contractor will be a contractor for the complementary set x. So C in is a contractor for the complementary set of x, whereas C out is a contractor for the set. Okay, so now to CVR I will not give test, inclusion test, or I will not give it inclusion function. I will provide to the power, CVR, I will provide contractors. Okay? Listen. So now let me come back to my problem. this, I will take C, the outer, so outer, will be equal to C1 intersected with C2 intersected with C3. I recall that I am able to intersect the contractor using some kind of contractor algebra. Now I want to find also an inner contractor. So how can I do that? I will do C bar, so a contractor for the complementary. I will write x minus xp square plus x minus square smaller than 22. I will dig in. Okay. Smaller than E minus or x square plus y is square bigger than the E plus. Lower bound, upper bound. So here, I will build a contractor for this one. I will build a contractor for this one. I will make the union of these two contractors. And I will obtain a contractor for the complementary constraints of this contract. Then, I know also that the set S, so my solution is something like this, is X, and I know that X bar, it will be not the intersection of all, so it will be using the De Morgan rule, you will obtain that the complementary set of the intersection is the union of the complementary set of each xe. So I will obtain a union of two unions. For each set, I will build a contractor, and I will obtain a contractor for X bar. Using, so what you have to, what I wanted to say is that we are able to, using union and intersection of contractor, we are able to build inner contractor so that we will be able to characterize inner and outer solution for sets. Okay, just to illustrate why contractor algebra can be useful. So now, when I have outliers, I have finished with this example. When I have outliers, so I have here two, for instance, P1 and P2, two unknowns, and here I will have measurements. T, here Y. Remember that when I have here the parameter vector, which is here, will correspond here in the measurement set an output. I will perform some measurements, first measurement, second measurement, third measurement. If it is a true solution, then it is an outlier. Each measurement corresponds to a set here. I will call it, for instance, x1, the one which corresponds to the first measurement, x2, which corresponds to the second measurement, x3 to the third measurement, which is an outlier, and x4 like this. Now, of course, if I intersect all these sets, I will obtain most of the time an empty set if I have outlier. So what I want to do is to use a contractor approach to be robust with respect to some outliers. So why it is important in practice? Because when a robot is moving inside an uncertain environment, it is supposed to measure distances, but when you measure distances, some people are going just in front of the robot and you measure another distance. When you use a sonar approach to measure this distance, you will have some kind of specular reflection which gives you another distance. So most of the time, when you have a robot, you have outliers. So if I have 3 measurements, if I allow 1 outlier, it means if I want to be robust with respect to 1 outlier, it means that I will build the contractor, which is given by this expression. So let me illustrate here what is represented. I have a set, and I have a set. The intersection of the 3 sets is empty. If now I have here x1, x2, x3, if I want to belong to 2 of these sets, it means that I will make the union of this intersection between x2, x3, between x1, x2, between x1, x3. So if I want to represent in the machine this set, most of the time it will be the set will be represented by contractors. Using this expression, I will be able to represent what we call the relaxed intersection, where we are allow one contractor to be unsatisfied. Okay? So, just to illustrate what happened here, I have 6 sets given here. The intersection between the 6 sets is empty. You can see it is impossible to belong to these 6 sets. If now I try to relax 1 set only, the intersection is still empty. You should see that it is not possible for any point to belong to 5 of these sets. If now I want to belong to 4 sets, it is possible. So I relax 2 sets, 2 here. If I want to belong to 4 sets, that I will be here. If I relax 3 sets, I will be here. 4 sets, I will be here. If now I relax 5 sets, where I will be?
All space.
In all of them. And if I relax 6 sets,
Space, all the space.
all the space. Good. Okay, so R2, the union, and the empty. Okay, so you understand what is a relaxed intersection. So now a small exercise. How to compute it? Is it complicated? Do we have some kind of combinatorial explosion when we compute the relaxed intersection of sets? In fact, no, and I will try to explain why. So first of all, a small exercise. I will ask you to compute this one. This, the first one, this one. So I will ask you to compute this one. How will you do? Do you have an idea of where I will be? So you understand the question? Okay. So it's not easy. It's not easy. You have to think on it, but you will see that if you, with a nice method, you have done this. So it means that the intersection between all is empty. If I relax 1 set, 3, 4, it's not easy to explain, but I will explain it. Now, here, of course, I will take the interval envelope so that I will have only intervals. But how can I compute this efficiently? There is a special way to do it, and I wanted to show that computing the relaxed intersection of n intervals can be done with a very low complexity. So there is no combinatorial problems. How can I do this? So it is simple. First, I take all bounds, 1, 4, 2, 4, 2, 7, and so on, and I will sort them as follows. 1, 4, and so I